Right, so we're back now, recording. So we've got this term here, and this is a rational term, so x it's rational in x. So this is 1 over x times 1 minus x squared. Okay, so 1 minus x squared, this is 1 over x times 1 minus x times 1 plus x. And of course, this is like we know how to do these things. This is ax plus b1 minus x plus c1 1 plus x, and these are very easy to get. Either you compute the common denominator, or you just use residues, because these are, if you look, x 0, 1, and minus 1 are simple poles of this rational function. Okay, we can still call them poles. Okay, so that means that a is limit when x goes to 0. Okay, from x times 1 over x minus x to the power 3, and this, the x goes away, and then this is 1, and then b, and so on. Okay, and then you take the integral, and then you can compute these things yourself, and you can use them. I can use these things for assignment and ask you how to fix them. Then you can solve them in Maple, of course, or you can solve them in MATLAB. Okay, and then I can ask you things about this stuff. What I want to show you now, what I actually want to show you, one other nice example is this one. Where is it? I've got another example here, and we can solve some of them the next week. We can solve some of them next week. Yeah, this is also a very nice example you can use here. X dot is 2 square root of x. This is also very nice to compute. Okay. But now I'm going to shut the screen here and go back to the screen of MATLAB in this one here, because I think MATLAB and Maple are more important than at this point than the other ones. Okay. So, oh no, I think I made it wrong this time. This is not right. So we go back here. We take this here, and then we start. No, I'm going to do this. Okay. Right. So now I'm sharing the screen. Okay. Now I also found a very nice example online today, which I think it's nice to show, and it's also a preview of things we are going to talk about a little bit later. I found online this very interesting examples of the predator-prey model, it's called. Okay, so the prey is hunted by the predator, who's the hunter. Yeah. Oh yeah, one very nice thing. How do you usually call the thing that you hunt, the object of the hunting, whether it's an animal or a man, in English? Do you know how you call this? Do you know?
Yeah, it's called prey.
No, the prey is the object once you want to eat, sort of. But how do you usually call these things in English? The result of the hunting is called, the object that you hunt down is called what? Prey or?
Catch.
No, game. Prey or game. Game is called in English. Look this word. Look up this word on the Oxford Dictionary. You can find online. Game. Okay, and that's why the English usually, when it's an easy catch, when it's a very easy prey because it's exposed. When something happens to someone, even usually a person, you've heard the expression, he was fair game. He had an accident, but his car had troubles anyway, so he was fair game. You hear this expression quite a lot. It's very interesting. But this model is also quite nice, and Volterra was a famous mathematician. I don't know who Lotka was, but they built up this nice model that you can see here. There are two differential equations. Okay, so this is a system of equations. I wanted to show you because we are not talking about higher order systems at the moment, but we'll talk about these things next week or maybe in 2 weeks. Higher order systems are systems of ordinary differential equations of order 1. So the degree, sorry, of the equation of the differentiating, the differentiation happens only once. This is very nice because MATLAB knows only how to integrate simple equations, first order equations. I don't think MATLAB knows how to integrate. I have to look this up because if it does, maybe I'll show you next time. I'm going to look this up. MATLAB does not know how to solve a second order differential equation. Maple can. I'm sure Maple can solve higher order differential equations. But MATLAB, as far as I know, cannot. So you have to build from a larger equation, from a higher order equation, you have to build up a system of more first order equations. Okay? And here you can have the model. You have the model here. Yeah. Here P is the state of the system. So P is the integration variable, and you've got P1 and you've got P2. If you can see here, can you see here? You've got P1 and you've got P2, and beta probably is a constant. Yeah, beta and delta are constants. Okay. Right. So this is how you define the function of the function for your differential system, and this is what usually is done in MATLAB. In MATLAB, usually you build up a special function for your differential equation or your differential system, and then you separately build up another script for the integration. Is this clear? Do you understand this, what I've just written here? Yeah, I got this from the internet. This is not mine. I didn't build it. This is from the internet. But you can use this, and you've got all these scripts uploaded on Moodle, so you can always check them out. You can always use them to sort out your assignments. Right. Now we go to the integration thing, and here we have the initial time, which is 0, and the final time, which is 15. So this is what we this is the interval for integration. Okay, so here they build it differently. They don't use lean space for this one. And then you have the initial conditions. So you have 50 predators and probably 50 prey. This is what usually means. Okay. And then you do the integration. As you can see here, you can do integration for the whole array or vector of states here. So this is the state vector P. P has P1 and P2 as components. P1 and P2 as components. And we use the same ODE 4.5 Runge-Kutta based numerical integration. Here is the reference to the ordinary differential equation, the pointer, I think, or what's this called in programming? I don't know. It's using the variable of the differential equation. This is the time to integrate, and this is the initial condition here. Okay, and then we do the plot where we see the population and the prey or the predators. In the second plot, we'll see something very special and peculiar to nonlinear system, and this is called a phase plane, because we are going to build one state depending on the other. So it's going to be prey versus population versus predator. Okay, and see how this evolves, because this is what we're interested in the final, in the end. Okay, how this is happening. Okay, let's run this. Let's run this system. I'm running it. It's taking a while. Just bear with me for a minute. Oh, here come the plots. Okay, so look, figure one shows the evolution over time of the prey and of the predator. In red is predator, in blue is prey, and we can see what can you see? That they have a periodic. Can you see that they have a periodic evolution? They have a period. Both of them have a similar periodic evolution, and if you can see, this is constant. Can you see this? It's constant. The periodic evolution is constant. Okay. How does it look like to you? Is it stable or unstable? How does it look like? So if you start with equal initial conditions, let's just increase, and let's just put this 50 and run the simulation for a longer time. See what happens. Yeah, look at the evolution. So this is constant, right? This is constant. You see that? You see that? So it looks like a stable evolution, true? But it's oscillating. These are oscillations. You see that you start from 50 in both cases, and this is the prey, and these are the predators. Okay. It looks like it's stable. Stable and oscillating. Stable and oscillating. Stable and oscillating. This is quite interesting, isn't it? It's stable and oscillating. Let's look at the second. Let's look at the second phase plot. Okay. And we see that no matter what happens, it's always the evolution. The evolution is always in this circle. So this is predators. Yeah, here is predators versus prey on this line here. Okay, and this circle is always constant. What nonlinear phenomenon do you think this is from the ones that we have talked about? What kind of phenomenon is this? This is also typical nonlinear. This will never happen in the linear case. What phenomenon is this? Can you tell me? Huh? Can you explain this phenomenon? Do you know a name? Have you got a name for it? What's the form of this? What's the shape of this thing? It's like a circle, right? It's like a cycle. So what kind of nonlinear phenomenon do you think this is?
It's a basin of attraction.
Yeah, but it's a phenomenon. This circle, we have talked about nonlinear phenomena which are peculiar to nonlinear system. Isn't this a limit cycle?
Yeah.
This is how we used to call it, a limit cycle. The systems trajectories will never leave this circle. No matter what you do to it, it's always going to be a circle. It's always going to be a circle. And the solutions of the differential equations are always going to be led by oscillations. These are, we call them, and we'll see about these things, we'll formalize this properly. These are called structurally stable oscillations. Structurally stable oscillations. Okay? So what happens now if we change the initial conditions? Make them 10. This is also 10. So we decrease the number of these things. You see, it's the same. It's the same type of oscillatory-like behavior. Oscillatory-like behavior. Now let's see what happens if you put more predators over a smaller number of. Look, you see, more predators or more prey. What is this? What's this more? Prey. No, it's actually more prey this time. More prey. If you put more prey and the same number of predators, the behavior stays the same. Now let's increase the number of predators. Look, behavior is the same even if you have a larger number of predators. You see? So these are limit cycles. These are limit cycles. Okay. We should also, what we should do here? We should say over this one. Hold on. I want to see more things. And let's go back to the main command window of MATLAB and clear all. Yeah. Now MATLAB is cleaning up the workspace and everything, and we're just going to restart the simulations with several diverse, I would say, initial conditions and see what happens. Right. This is this, and this is. Let's run this again. You see? And now let's change the initial conditions. Let's go back to the 50-50. Look, you see? Smaller cycle. Because now the number is equal. Number is equal. But still, the cycle is the same. Never changes. Now we increase this. Look, this is a large number of prey. Okay? Now let's see what happens if one of them is 0. It doesn't happen much. You see, the cycle is gone. You see, so if there is no predator, that this is a natural phenomenon. You like it? This is very funny. This is natural phenomenon. If there is no hunter, then the prey goes to infinity. You see that? So at a certain point, if there is no hunter, the prey has the evolution of the prey has a finite escape time because it's too much. Let's simulate more and see this. You see? You see? So there's always going to be, so the prey it becomes too much. Okay? The population of prey is booming. Okay? All right. Now let's put some predators. Even if you put a limited number of predators, look. Even if you put a limited number of predators, you still get the proper answer for this. Okay? Even if there is a limited number. Now let's have no prey, and only predators. Let's have 10 predators and no prey. Oh well, look. The predators disappear. The predators disappear. Okay? The predators disappear if there is nothing to eat. Do you agree? Do you agree? The predators disappear if they've got nothing to eat. This is what this graph shows you. Yeah? Okay? Even if you put one predator and no prey, even if you have one predator and no prey, that predator dies out after a certain period of time. Okay? Right? So the idea is to have both predator and prey. And then there is a cycle of life. I think we can call this a cycle of life. Can we call this figure 2 a cycle of life? I think we can. You agree?
Yes.
Yeah. So this is very interesting. Let's see how this looks. Okay, this is a system. It would be interesting to see how it looks in Maple. But in Maple next week we are going to talk with another example called the population of fish in a pond. Okay, we're going to talk about the population of fish in a pond. Okay, I think this was an interesting talk, huh? We'll do this. We'll show this example again when we talk about second order systems. You agree? Okay. If you have questions about everything we discussed today, if you've got questions. Any questions, please? Do you have examples or anything you'd like me to show you? You got any questions?